we now looking at the mathematical description of the simple harmonic motion. Okay, again, as when we want to analyze the motion, we have to start from the force acting on the object. Okay, in our case here we have the spring attached with the object, and we measure the distance of the object from the equilibrium point that we denote it as the x is equal to 0 here, the equilibrium point. And if the object has a mass m and the spring has a spring constant k, and we assume the perfect or the ideal spring, that the force is exactly equal to the minus of kx. It follow the Hooke's law. And also we say that there is no friction between the contact at the contact between the object and the surface. Okay, no friction. So the only force act on the object now is the restoring force from the spring, and we have the equation. We have the equation for the force is F equal to minus kx. So we can then use the Newton's second law. F equal to ma equal to the md square x by dt square is equal to the minus kx, or we have that d square x by dt square is equal to the minus of k over m x. Okay, so we have the equation, this differential equation to solve. Okay. We may solve this equation directly, but here we will guess what should be the solution of this equation. You can see from this equation that we need the function of x to be differentiated twice and give the same form. Okay, you can see from this equation that when we differentiate x with respect to time twice, it gives the x back with the constant in front of the x, this minus k over m here. So what we want is that the x is a function that if we differentiate twice, it will give the same function back, okay, with maybe some additional constant time that function. Okay, so the first condition is that different differentiate differentiate to time. And we give the keep same functional form. Okay, differentiate 2 times, keep the same functional form. And the second, X should exhibit the oscillation, so it has to be the oscillatory function. Oscillatory function. From the basic calculus, you can see that the function that match these two conditions is the X should be the, we call it the sinusoidal function. The sinusoidal function, we have two kinds of sinusoidal function. That is a sine function or cosine function. So x should be expressed as a sine function or the cosine function, which is both the sinusoidal function. Okay. We can show that x can be expressed in terms of x is equal to the a sine omega t plus phi, or x is equal to the cos omega t plus phi. Okay, both forms are valid. You can use any form, sine or cos, but we will first use the sine function first. But please remember that we can use sine and or cosine form of x. We can use both. In this expression, we put omega is equal to the square root of k over m. Okay, and we call this omega as the angular frequency. Okay, this is the angular frequency, which is related to the frequency we have that omega is equal to the 2 pi f, where f is f is a frequency. F is a frequency. Okay, and we call phi is a phase constant. Phase constant, and A is the amplitude of the oscillation. Okay, we will talk about the physical meaning of the three parameters. Okay, let's see the detail of the physical meaning of the three parameters. Is omega and f, what is phi, and what is A.